Welcome to the Future Tech edition of the Finding Genius podcast. Forget frequently asked questions. Forget common sense, common knowledge, or Googling for information. How about advice from a genius in their field instead? 95% of people in any profession are good enough to be qualified and licensed. 5% go above and beyond. They become very good at what they do, but only 0.1% are the geniuses of their profession. Richard has made it his life's mission to interview the geniuses of their fields in areas such as AI, 3D printing, quantum computing, blockchain and Bitcoin, and more. Don't miss out on amazing podcasts with geniuses. Review us on iTunes or wherever you listen, and go to futuretech.findinggeniuspodcast.com and subscribe today.
Hello, this is Richard Jacobs with the Future Tech and Finding Genius podcast series. I have a returning guest, in.Paulsen. He works at Xometry, Xometry. He's the head of applications engineering. And last time we talked about how Xometry helps facilitate companies that want to manufacture various parts to find the vendors that will do it for the best price and the fastest and the most reliable, etc. And we talked very briefly about 3D printing, but we didn't go deeply into it. So that's what this interview is about. I have a lot of interest in 3D printing. I know listeners do as well. And there's hype, there's reality, there's, that dream of at home, like Star Trek, having this replicator that can make anything you want. So let's find out what's real. So Greg, thanks for coming back. How you doing?
Hey, Richard, really happy to be back. And yeah, I know after our conversation from the last recording, I think we had like an equally interesting convo about 3D printing. And I'm excited to be back and be able to talk a little bit about the technologies and what you could do with it.
Yeah, I've spoken to 3D printing companies before, but I would guess you have a nice 10,000-foot view of the players and what they're doing and what's possible. And I know some do metal, some do plastics, some are trying to do composites, et cetera. But like, what's your general feel? We're here in 2020. What's your general feel of 3D printing? What is it capable of doing, and what's still futuristic for it?
Yeah. Well, I think a lot of people don't realize this. So 3D printing has actually been around since the mid-'80s. So a technology called stereolithography was invented first, which was this curing of a photopolymer and turning it into a rigid substance by basically exposing a UV laser to a specific point. It solidifies that, and the material is almost like the same material they use when you do like you get a cavity filled or something. They do that little UV cure in the back of your teeth. It's that same material where it cures and hardens over time. So some of these processes are much more mature than other processes out there, but there's always these strengths and trade-offs with additive manufacturing. Since I work for Xometry and we are this manufacturing marketplace, so our goal is to make quality parts fast, and that means that we need technologies that are actually reliable and resilient. And it also means I have the benefit of taking an agnostic approach on additive manufacturing technology. So we're offering 7 umbrella technologies around additive or 3D printing, both in plastics and metals at Xometry, and all of them, they need to perform. And none of them are perfect, but they're, some are, much more mature than others. So it's quite a diverse array of different tech, and I could go a lot of different directions.
Yeah, well, again, let's talk about first, what's the fantasy of 3D printing, and are there any elements of it that we're even close to?
Yeah, so this is the fantasy. So I work in traditional manufacturing as well, like injection molding, CNC machining, and all these require some level of setup. So even the buttons on your shirt, they are injection mold plastic pieces, millions upon millions of them made. But every single time you have a new design for a button, it requires a new mold. So it's a new metal tool that has to get machined to essentially the negative of that design. Special tooling's made, and then you have to set up in a press and create these parts, one by one, or sometimes in small arrays. But you have this fixed cost and this fixed work up front. The beauty of 3D printing is that the net material, the material that you're using to actually build this stuff with, your parts with, is amorphous. It's a powder, or it's a filament, or it's a liquid resin. And through this machine, these different machines, they're actually able to harden or cure or fuse these materials together to build this three-dimensional object without the need of initial setup. So 3D printing allows you to kind of reduce that barrier to entry in manufacturing, where you can just make that part. Or you can make 1,000 buttons that are all a little bit different. They all have like your initials in it or something. And the machine doesn't necessarily care anymore. It's just doing its job and taking the next digital file and translating that into a physical reality. So that the grand scheme of this is that 3D printing, it's not just another manufacturing technology, but it's a much more accessible technology. And with the ability to make it more repeatable, you could then kind of take this technology and move it to different places distributed and have more localized manufacturing sources without the need of technical specialty. So it allows you to distribute manufacturing more, which is a very interesting concept.
When do you think that a regular person, a regular consumer will be able to go somewhere and say, hey, can you make me this? In the old days, and still, can you make me a key for this house or this car? And you go to Home Depot and get it done, which is like a lame form of 3D printing. But when's it going to be more sophisticated, where you can go to like Home Depot, Lowe's, or somewhere, and they can make you something right then and there?
So, I think there's going to be a mix. I can tell you at Xometry, we have this distributed network of all these technologies, but every single one of these processes, and this is kind of like the hidden factor in 3D printing, they require 3D CAD design. So that is a generated three-dimensional model. So you're building your object on a computer interface. And that design is essentially what the machine is reading as blueprints. And very often, we have your key. What they're doing is they're tracing a different key and they're making a key based on that. So you already have that profile there. But a lot of times, what's not realized in that product development process, where I have an idea, let's make it now with a 3D printer, is that CAD design. Something that I've seen over the last decade is the accessibility and the cost. So the accessibility of CAD programs has gone way up, and the cost of CAD programs has gone way down. And I think a lot of that is attributed to the influence that 3D printers, including desktop platforms, so these consumer grade machines, has really brought on. Is these guys have great printers, and they're like, wait, I need to make a design, and I don't have the software to do it, or I don't have thousands of dollars to buy a software to do it, and the software's been catching up for them. So it's a really interesting balance, because the printer is only as good as the CAD output, and the software can basically dictate to the printer.
Are there standardized software platforms that are coming up now specifically for 3D printing that are better than others?
Yeah, well, I use, so I've been modeling in SolidWorks for quite a while, which is a professional engineering grade platform. And there's a kind of Autodesk has Autodesk Inventor, and PTC has Creo. And there's a lot of these engineering grade formats that are very, very powerful and very useful for engineers to develop with. There is also consumer end, I should say prosumer end, softwares that are more accessible for students and people who are learning, that are still have a lot of powerful tools to generate a design, and not just a design, but a design that you're intending to do. Because sometimes you do have to make trade-offs with like really, really low end or introductory software. So I've been liking Autodesk Fusion 360 and Onshape as two platforms where I can get a very low barrier to entry, a lot of times free trials or student versions, or like a very, very low cost to get in, yet a very powerful platform that is nearly as good as some of these software platforms that you use in the professional engineering world. But those literally didn't exist 4 years ago. Like these like the CAD design accessibility is a technology in itself, and a lot of it hadn't existed for years. So now we're seeing this explosion of people that are able to design a part good enough and dangerous enough sometimes to be 3D printed. So they may not have any traditional experience like an engineer would have in designing, but they get enough to 3D print their design, which is a much more forgiving manufacturing process in regards to design freedom. So it's a really interesting side story with 3D printing, is that CAD can empower you a lot more, and then the technologies are there. And again, we have accessibility to plastic and metal printing, so there's a lot more this cool stuff happening in the 3D printing world.
So maybe it's obvious, but why print in metal? Why print in plastic? Are there hybrid printers out there? What are the use cases for the different materials you can print with?
Yeah, so the most common materials that you're probably going to be printing with, especially if you're on a semi-commercial scale, are going to be materials like nylons. They're really popular, and there's a couple technologies that can mass produce nylon parts really cheaply, particularly something called selective laser sintering and HP multi-jet fusion. Both of those take essentially a flour-like powder. So it's a nylon material, and use a heat source for SLS, so laser sintering. It's using a laser to fuse cross sections together, so it creates little micro fuses, creating the shape of the part. And eventually we'll build the parts from bottom to top, kind of suspending them in the unfused material. For the multi-jet fusion platform, it also has a heat event, but in this case, it's using essentially a fusing agent that then gets exposed to heat, and that agent absorbs more heat, creating a melt at those locations. But each one is going cross-section by cross-section by cross-section, building parts up while suspending them in essentially unused powder. So when you're done with these machines and the parts are done, you're digging through them like a treasure hunt, picking out your parts, and you bead blast them off, and you get really functional, useful parts. Like nylon's a very flexible, chemical resilient material, has good heat and temperature resistance. So it's a really good general purpose one. I call it the 85% tool, because it usually brings you the 85% of wherever your project's going to go, because it's just such a useful material. Surface finish is a little bit more matte. It's not smooth like a molded finish, but it's something that you can work around with different post-processing. The other more common one is going to be something that along the lines of ABS or ASA, which is usually done through a filament fusion process called fused deposition modeling. And that's kind of the classic desktop 3D printer that you may see, where you have that a reel of material, so this like long strand of filament material, and it's basically melting right at the end of that strand and then depositing it on the part object that's building and zigzagging back and forth and building the part from the bottom to the top. The beautiful thing about that filament platform is you could just change out materials. You have to tune it a little bit to what heat, temperature, and other environment factors you need, but it's boutique printing. So I need yellow filament for this one, or I need glass fill, or composite fill for this one. And you could change out these materials very readily, where these more nylon powder bed processes are really dedicated machines. They're powerhouses producing 30 to 300 parts per night, but you're kind of dedicated to building a nylon. Metal. So I build those for plastic iterative prototyping. Plastic is cheap. It's easy to modify. Like I said, you could sometimes get a really good economy of scale making those parts. It's a different story when I talk about metals. So metal is not a commodity. It is still, the pricing has gone way down. I know Xometry has extremely competitive pricing on metal 3D printing, but it's still sometimes an order of magnitude more expensive than the plastic counterparts with the same design. So there's a few reasons why you're doing that. First off, the machines are typically more expensive. So I may be making a part, say, in like 17.4 pH stainless steel, which is a nice hardened steel that is corrosion resistant, very good multi-purpose. It can be sterilized, used in a lot of different applications. But yeah, I'm building this part. I'm literally fusing it to a steel build plate to build it. And I also have sacrificial structures that are holding what are called overhangs on this part that I need to remove. And that is made out of the same material. So everything I have to do to post-process in what I do in metal 3D printing needs to be stuff that cuts metal. So if I'm running a machine in plastic, like I said, I can usually just take my hands and peel off sacrificial structures or sand it down. But when you're dealing with metals, you need a machine shop to really properly process that. So it's one thing to build a part in metal, but it's a whole nother thing, and sometimes more of a thing on the post-processing side with metal 3D print parts. And that's what I wanted to ask you in general. Plastic, metal, whatever you print from, how much post-processing is needed to remove burrs and finish a product to make it look ready to use? Well, so I'm a person who loves the layers, right? So I've been building in additive for over 12 years now. So I've come to appreciate these layer lines, which is this look that parts have because they are built cross section by cross section, kind of stacking on top of each other. That being said, to make it smooth, you really do have to do several more intensive post-processing. So for those powder bed systems, like those nylon parts, a very common finish that we'll use after we bead blast, which will remove any excess material, you have this almost sugar cube-like finish. And I may media tumble that to bring that sugar cube to like a satin finish. And I could dye it, give it different colors. So black is most common, but reds, greens, blues, you name it. You essentially are dyeing with an acid-based dye, so similar to what you do if you're tie dyeing a shirt, and give it some color, some pop to it. But if you wanted to bring that to a full smoothness, there's a couple options. You could go further abrasion. So like I said, with that media tumble, which is an abrasive process, you can go sand, smooth, and all of a sudden you're putting a lot of manual work into something that was completely digitally created before you touched it. So your scalability goes down. Or you can use some of these more novel processes. So there's some post-processing technologies that have come out recently that are using a vapor, it's a physiochemical process that will actually go and surface smooth without you personally interacting with it. So you're basically racking or hanging these parts up in a pressure-controlled environment, and then exposes the parts to something that honestly has enough of a reaction to the part to actually smooth out those surfaces. So if I'm doing that with ABS, I may be using something that's acetone-based, for example, because it's chemically weak to acetone. And so it'll actually kind of like melt and smooth out the outer sides. When you're using nylons, it's some sort of crazy concoction to do that finishing, but you get a really interesting result because it looks closer to something molded where it has a little bit of a gloss to it, and the surface is sealed. And that's newer technology that's been coming out like this year, really. So it's still in an early stage, but I think it'll become more and more common as we move down in additive manufacturing.
So what would it take to 3D print something, do the post-processing, then do the finishing with, paints and everything else, if paints are needed or some kind of gloss or whatever, to, a full finished part? Do you think that'll ever be the domain of 3D printing, or it'll be the workhorse in the background that gets the parts to that point where the finishing is done for the assembly lines?
Yeah, so let's talk about where we are now. And, we are pumping out additive manufacture parts at Xometry. So this is something that is, one of our specialties. And we, like I said, we have all these different technologies. Different processes have different surface finishes to them. So like I said, those commodity materials tend to be very cheap, but they also do not have that gloss, smooth surface finish. So you could enter the market with a small part that's, $9. But the second that you have someone, doing a manual action like sanding, smoothing, painting, you're paying for labor, and that labor could be significantly more than the cost of the part to do that. So that all these touchless technologies are much, much more viable to your point, to the scale of the future of this, where you're going to start building work cells that are closed loop and able to essentially take apart from that net blank finish that comes out of the 3D printer to a cosmetically beautiful part in between. And that's still really in early stage development of what's coming out there right now. I could say that some of these resin-based printers, so stereolithography, like that early stage, I said around 1984 invented, those have a more of a liquidy look to them. So they have a smoother surface finish from the get-go, and they tend to take paint easier and tend to post-process more easily than these other materials, but they're not as robust. But what's getting more exciting to me is that there's materials like, for example, the process made by, the brand name is carbon. There's actually not carbon in these parts here, or carbon fiber at least. But carbon has a process called digital light synthesis that grows a part, like you're running in stereolithography, where it grows from a liquid resin, but then cures into a much more robust engineering material that is a long life material. And you have that surface finish that comes out more cosmetically beautiful from those parts. So I mean, the answer is, I don't actually want to paint parts. I don't actually want to, manually sand them. My my look for scalability and bridging that gap between prototype and, cosmetic model making and going towards a production viable, low cost parts using 3D printing has a lot to do with the combination of processes that can provide better surface finishes while actually providing better mechanical value, or integrating automated post-processing into the workflow. So every time you have someone touch a part, like every single time, I'm not sure if you've ever polished a headlight before, but if I want to take a clear 3D print through, for example, for SLA, the material prints clear, but the surface finish makes it look matte, just like you have a foggy headlight. And if you ever have polished a headlight before, you'll know how much labor that takes to take it and go from coarse to finer grit to finer grit to finer grit until you have a very high polish on that. And you have to do the exact same thing with those parts. And that's just time. That's your labor rate. It has nothing to do with the part anymore. It has everything to do with labor. So removing that labor rate from additive is key to making more cosmetic features. And like I said, or you could be like me and love the layers. And I think the world is getting much more used to seeing those natural build lines in some of these additive parts.
So what do you think is going to be possible the next few years for 3D printing, where people will see this commercial effects? And what do you think is a little bit further future, maybe 10 years, but really impressive, and you think it's coming?
Well, let's talk local news. The new, I think, 777 or 787 model has over 300 unique additive manufactured components in it right now. So these are commercially used additive manufactured components. They're highly specialized, highly tuned, and these are made up with dedicated machines for this factory, but they're utilizing that advantage of complexity without increased costs that additive manufacturing could offer. So additive manufacturing is being used regularly. If you have, if you ever have a like hip replacement, knee replacement, you probably have an additive manufactured part implanted in you. So there's a lot of viability in additive, and of course, like it's a king of prototyping because I have no setup fees for that. Moving to the future, though. I think there's going to be a much larger merger between software and machine and the feedback loop that they have with each other. So a lot of times when I talk about additive, I talk about it's building a net shape. It's the machine doing its darndest to make the shape of your part in whatever process it's doing. I think with better closed loop systems, it's going to start self-correcting and getting closer to what you modeled. So you don't have small, like minor discrepancies in tolerances or feature sets on your parts. Like I said, that's the whole printing process where the method in which you're prototyping is also the method in which you'd be making production is extremely interesting from an additive standpoint. So that process I mentioned with carbon DLS, where it is making a part that if I just made one, it's still as viable as the end use production unit if I'm making 10,000 in that process, or metal 3D printing to that matter. I mean, that's metal. It is solid metal parts. I mean, they're not something fluffy where you cut inside and you see voids. I mean, it is solid metal. When you cut into it, it cuts like billet material. And truthfully, when you start working on a process where you're using 3D metal printing, your initial concept designs, if you're using that 3D metal printing to start your prototyping, is going to be that same material that you may ultimately build your parts in production with. And I think that's a very interesting goal for anybody building additive manufacturing platforms is, can I prototype this and will someone be able to take the same technology to a production level? I think it's very, very interesting. And just from your standpoint, like some of these parts are not, they're not cosmetic, but they're still extremely mechanically viable. And I think something you're going to start seeing more from larger brands, commercial brands, if you're talking GE or these other companies, is the availability of a digital library of parts for replacements as an alternative to buying replacement parts. I think will be one of those things that we're going to start seeing more often than not, because you still have mechanically viable parts. They may not be as pretty as the molded pieces, but they could be near instant satisfaction or gratification from being able to take your desktop printer and just make a replacement on the spot.
What about making much more lightweight parts or designs with voids where there can never be voids, or impossible parts? Is 3D printing getting better at that? What are the use cases?
Yeah, so particularly for powder bed processes that are doing a fusion event of those parts, you get very unique complexities out of that. And so lattice structures are very common when you're looking at building a structurally sound but lightweight design, and you're using 3D printing, because lattices are able to form with these processes because you're basically growing one feature on top of the other without worrying about a kind of a line of sight, like a directional cut, like you would with traditional CNC manufacturing, where you're drilling into that part. And yeah, you're absolutely able to do that. And keep in mind, we're talking, can the printer do it? Yes. Does software enable it yet? Not great. It's software is catching up on that. So you see some amazing stuff coming out if someone has a robust enough software. But the accessibility to software to apply things like lattice structure or that optimized geometry, that's called topology optimization. All of that has really specialized software that is really cool when I see it applied. And the best parts we've made have been made with this type of design software. But the accessibility, it's still at an upper echelon versus a lot of these introductory CAD programs where a lot of people are still playing and building their designs through. So you don't see it as much as I'd really want to, because the machines are absolutely capable of developing these designs and these geometries right now. I'm also really interested in texturing, so being able to select a face of a part and apply a texture, like a diamond grid pattern or something like that. I think that actually helps make some of these parts that have less cosmetic faces naturally look a little bit better by creating almost an even, purposeful texture across those parts. I think that's actually a new piece of technology that we'll see more and more. And again, all that is software driven. It's actually not the printer. The printer is already pretty capable. It's about bringing the software and bridging that gap, which is actually more important for the next couple years in additive manufacturing.
Well, how hard is it for professional grade software, the stuff that you have? Can it do it? Or are you talking about the more hobbyist software, those features are missing, or is it missing in general?
I think they're still lacking. Like I said, SolidWorks has topology optimization packages. I know Siemens has a great package for doing this type of work, and a lot of these technologies are out there with design add-ons, but they're not inherent in the base package of the CAD program. So unless your job is doing mechanical lightweighting via topology optimization, a lot of times your accessibility to that software platform doesn't exist. Like you don't have it yet. There are some mesh manipulation softwares that will take a mesh file of what you've generated with your CAD design, and mesh is essentially a file format that can be interpreted only by 3D printers, and it's also the same file format that you may use for 3D animation, for example, where you don't need solid. It doesn't need to be solid. It just needs to have an outer face to it. And some of these mesh manipulation programs can incorporate things like lattices and different infills and different structures to parts. But again, they're not cleanly joined with traditional CAD software. So I think that's still something that there's bridging. And again, if you do a Google search right now and look for, topology optimization or lattice 3D printing, you're going to see a lot of softwares out there, or you're going to see a lot of add-ons for traditional CAD packages. But there's not a lot of CAD right now that just has as a default saying, hey, I'm 3D printing and I want to grow my part in this orientation, generate this section into this type of lattice structure. It's not as straightforward as I hope it will be soon.
It is probably like a very strange area of it, but is there any biomimicry, anyone with a fascination for using 3D printing to create models of living things that are far more accurate?
Absolutely. And I think that's when we're talking about lattice structures. We're talking about growing parts. I mean, we are not subtractively made people. We are not subtractive organisms. We are additive. We are 4D additive, if you will, because you have cell growth and multiplication. But we are growing. We are growing bit by bit on top of each other as we're, as humans or any life structure is built. So additive is much more analogous to organic growth than traditional machine cutting. When you're taking a piece of metal and taking a drill or end mill and shaping it and forming it, that's is a process that we're very used to and we're very good at doing from a technology standpoint. But organic growth is much easier to actually show off using additive manufacturing technology than with traditional manufacturing, where it would be a lot of surfacing. Actually, I think biomimicry is a very strong point when you're designing for additive manufacturing.
Interesting. Any other ancillary uses or uses that I haven't thought of, or people wouldn't think that I didn't know you could use it for that? Anything strange you run across are really cool?
Oh man. So a lot of times, I live and breathe in the world where I'm working usually in aerospace, professional engineering environments. So a lot of stuff we see is very straightforward, like, brackets, fixtures, things where the traditional way of doing it may have been like 4 or 5 pieces, but with additive manufacturing, I could just essentially merge all those features together and make it out of one piece that would be very complex and expensive to traditionally machine or mold, but very straightforward to 3D print, because again, you're growing those features out from each other. So a lot of what I live in is that mechanical world, and they're looking for, can I mechanically substitute what I've been doing traditionally with an additive manufacturing counterpart? So sometimes it's a surrogate for casting, so something you may metal cast for production. Can I substitute it with additive manufacturing? Absolutely, you can do that. And then, of course, that prototype to production stage where you're kind of testing your market and moving forward. I think one of the things to note is you have different fields of folks who are understanding additive manufacturing. Those who are using it are able to see different capabilities and often have like 2 or 3 technologies they really focus on, and may not even be aware of the other like 10 that are out there and available to them, as well as the array of materials. Some may not even know what's capable. So like I hope that some of your listeners today learned that you can 3D print metal, and it's a pretty common thing. You just need to have some rules behind it. But all of that takes that 3D CAD model to get started. And the power users are few and far between still. There's still so much that these technologies can do. But a lot of the knowledge is still tribal, where those who are using it have already kind of stubbed their toes, 20 different times on different projects, and have kind of learned along the way some guidance and tweaking to make their parts right. Something that I do at Xometry is I help write our design guides. So we have free online design guides for every technology that we offer, including the 7 additive manufacturing techs out there. And if you're looking to learn a little bit more, I really recommend checking out some of our design guides, because you'll learn a little bit about the process itself, as well as kind of the do's and don'ts, and what's great about this process and where the trade-offs are. Because like I said, nothing's perfect, but not even like traditional manufacturing is perfect in every way, shape, and form. So it's more about how can this be a tool?
Yeah, so as resources for listeners, that's perfect. Can we include a design guide, a link to it in the show notes? Mm-hmm. And then also, you mentioned offline an article you wrote about 3D printing in 2020, what's coming or what's possible.
Yeah, so definitely happy to share that in the meeting notes. But I recently wrote it's a little bit of a read, but it's what lies ahead for 3D printing in 2020, some trends, and a lot of it we've touched base on. So that's the software, the power of software, and software and simulation before printing and even during printing. The power of adding better properties to these materials. So we talk about what's isotropic, and that's basically any direction in which I'm pulling this part, does it have the same mechanical effects? And when you're building parts layer by layer, very often you're actually weak in the stack direction, so that Z direction. And so there's a lot more going on there that I write about. Of course, new materials, new processes coming out, silicone, ceramics, different metals, even printed circuit boards, and then the hybridization. So sometimes using an additive manufacturing part as a piece in your setup for machining or your injection molding, or even in your CNC machine, actually being able to grow material and then cut it away. So all this is coming out. There's some processes more mature than others, but the accessibility still isn't there. So these are some trends that I've been talking about for 2020 and beyond.
Okay, well, that's great. Well, Greg, You're the man for 3D printing. Thanks for coming back and being excited about it and making it interesting in an understandable way for the layperson. So those articles will be available, and then people could also go to Xometry.com, Xometry. Any other ways they can get in contact?
Xometry.com is definitely the best place to start for all our guides and resources. Again, my name is Greg Paulsen. You can find me on LinkedIn, or if you go through Twitter at XometryGreg. And also we do a lot of video education series as well on our YouTube page. So that's Xometry's YouTube page. But we have lots of channels to educate on. So definitely check them out.
Excellent. Greg, thanks for coming. I appreciate it.
Hey, thanks so much. Have a great day.
You've been listening to the Future Tech edition of the Finding Genius podcast. This podcast is information only. No advice of any kind is being given. Any action you take or don't take as a result of listening is your sole responsibility. Consult professionals when advice is needed. Review us on iTunes or wherever you listen, and subscribe today by going to futuretech.findinggeniuspodcast.com.